Hello everybody and welcome to FatalSec. Whether you are into embedded devices, mobile development for Android or iOS, or just curious about the latest ARM based MacBooks, this series is for you. Dive into the world of low-level programming, understand how ARM processors work, and learn to write and reverse engineer ARM assembly code. Perfect for developers or reverse engineers who are looking to deepen their ARM assembly skills. So let's get started. An important point to note here is that ARM has several processors that are grouped into number of families based on the processor core they are implemented with. If you observe in this table, I have listed some of the famous ARM processor families along with their architectures. Each family has their own set of features and limitations. We will be using this ARMv8 architecture throughout this tutorial series, which belongs to Cortex A family, which is a 64-bit architecture found in all the latest mobile devices. So make sure that you have a ARMv8 based machines such as latest MacBooks based on ARM chipset. If you don't have an ARM based machine, then you can either emulate ARM architecture using QEMU, or you can use any cloud VM such as Azure or AWS to get access to a ARM based machine. If none of these options work for you, then you can even try to do this directly on your ARMv8 based mobile devices. On my side, I am using emulated ARM based Ubuntu machine for this purpose. And if you want me to make a video on how I set up this virtual machine using QEMU, then do let me know in the comment section. Alright, with that in mind, let's dive straight into assembly language. So what exactly is assembly language? Assembly language is just a thin syntax layer on top of the machine code, which is composed of instructions that are encoded in binary representations, which we call machine code. And this is what our computer understands. So why don't we just write machine code instead? Well, that would be a lot of pain. For this reason, we will write assembly. For this tutorial, we are focusing on ARM assembly, which is much easier for humans to understand. Obviously, it's not easy as compared to other high-level languages such as Java or Python, but compared to what machine code is, which are zeros and ones, understanding assembly is relatively easy. So now we know that computer only understands the machine code, and we as human cannot understand this machine code directly. So there comes the need of programming languages, and today we are working with assembly language. Now obviously, because computer cannot directly understand assembly language, we need to convert this assembly code into machine code, right? And for that we're gonna need a tool which is called assembler. So let's install this assembler on our machine using sudo apt install arc64-linux-gnu. Hit enter. So it's already installed on my machine, that's why it's saying 0 upgraded and 0 newly installed. But if it's not installed on your machine, then it will automatically install it. Once this is installed, you will get arc64-linux-gnu-as, where this AS stands for assembler. Okay, what this assembler does is basically it will convert the assembly code into the machine code. Okay, and this takes .s file as the input, which contains our assembly code, and as an output it will generate a .o file. This .o file contains the machine code which the computer understands, but it's not yet executable. This .o file will be an intermediate file that will be linked with other object files and libraries to create the final executable. Okay, and for this purpose we're gonna need another tool which is called a linker. So this tool would have been installed automatically as a part of installing this package. To check that it's there, simply try executing this command arc64-linux-gnu, and this time instead of as we're gonna call ld. And if you get this as an output, this means that this linker tool is installed and it's expecting some input files. Okay, let me try to visualize this for you. So over here you see in the first block we have _start, which contains the assembly code, right? Let's say this assembly code file is hello.s. Then like I said, we're gonna need to convert this assembly code into machine code, right? And for that we are going to use a tool called assembler, which is our arc64-linux-gnu-as. This assembler command will take this hello.s as input and it will generate .o file, which is an object file which contains the intermediate code. Okay, then after this, to get a final executable binary, we gonna need to use the linker.
It will take this hello.o, which is our object file from the previous command, as an input, and as a result it will generate hello executable, which is going to be our ELF64-bit binary for ARM architecture.
Now, before diving directly into assembly programming, there are few things that we need to understand first, such as data types in assembly language and registers. For that, consider this very abstract computer block diagram. This is a highly abstract block diagram of a computer architecture. Here, the CPU or the processor is connected to the memory and input-output devices through a system bus, right? It's important to understand that the registers, which I will explain in detail shortly, are located within the CPU itself. This placement allows the CPU to access and read write to the registers much faster than accessing the memory through the system bus. So just keep this architecture in mind. And now let's come to the data types. Like any other high level programming language, assembly language does not have data types such as integer, string, etc. But it does support operations on different sizes of the data. It basically operates with raw binary data and the sizes of data units. So from now on, you can consider these data units as data types in assembly, which are used to tell the instruction what size of data is going to be processed. It can be signed or unsigned, word, half words, or even bytes. The difference between signed and unsigned data types are that the signed data types can hold both positive and negative values and are therefore lower in range, whereas unsigned data types can hold large positive values including 0, but they cannot hold negative values. Now, to understand the difference between these different data types, let's look at this figure where on the top we have a byte. A byte is the smallest unit of memory consisting of size 8 bits. So this one single block can store 1 bit at a time, and by combining these 8 bits together we will get a byte. Okay, these bytes are then used to form a larger data type such as half word or word. Okay, so in a 64-bit architecture such as ARMv8, a word is of 64 bits in size, which is equivalent of 8 bytes. Now you can guess what could be the size of a half word. Yes, it's exactly the half the size of a word, that is 32 bits, which is equivalent of 4 bytes, right? So I think that's enough about the data types in assembly language. We will get more into the details of it once we start working with assembly programming. Let's now understand the concept of registers. Like I mentioned earlier, so if you remember from that CPU architecture diagram, registers are the smallest and fastest storage locations within the CPU that are used to hold data temporarily during program execution. To understand the registers, let's move to official ARMv8 developer guide. Okay, I have it opened already in my browser. So as per this, we have in total 31 into 64-bit general purpose registers starting from x0 to x30. Okay, now you observe here that each register is of size 64-bit, which means that each register can hold up to 64 bits of data. So each register can be used in two modes, that is either in 64-bit mode where the whole register is used, which is denoted by X, okay, or in 32-bit mode where the lower half of the register will be used. So when we denote X, we are telling the CPU to use whole 64 bits of the register, which is nothing but a word data type. And when we denote register as W, we are dealing with half word, which is 32 bits of the register. So these general purpose registers x0 up till x30 are used during common operations to store temporary values. Then apart from these 31 general purpose registers, we have some other special purpose registers as well. So if we switch to this documentation, here they have mentioned that in addition to the 31 core registers, there are also several special registers, and these special registers are 0 register, program counter register, stack pointer register, program status register, and exception link register, which are denoted by XZR for 0 register, PC for program counter, SP for stack pointer, SPSR for program status register, and ELR for exception link register. Alright. And if we scroll down a bit, this is how we can denote these special purpose registers. So for 0 register, we can denote it as WZR if we want to use the 32-bit mode of the register. And to use it in 64-bit mode, we have to denote it using XZR. Then similarly, for current stack pointer, we can denote it using WSP for 32-bit mode, and for 64-bit mode, we can simply write SP. No need to put X in front of it. Then similarly for program counter, this is the only register which you have to use in 64-bit mode only. You cannot use it in 32-bit mode because this register contains the address of the instruction which is going to be executed next. And in a 64-bit architecture, the address of the instruction is of 64-bit always, and this program counter register is denoted by PC. Okay, similarly we have another register called SPSR. This SPSR register contains several flags such as zero flag, carry flag, overflow flag. For now, there is no need to go deep into it. Okay, so enough of theory now. Let's try things out by writing a real ARM assembly program. So I'm going to create a very simple assembly program that instructs the system to exit and sets an exit code to inform the callee why the program exited or terminated. Now you might be wondering why I am not using a simple hello world program. So the thing here is that unlike many other programming languages where the first program you learn is to print hello world, in assembly language, printing hello world require a deeper understanding of the architecture and memory management such as stacks and heaps, which we will cover in the upcoming videos. So that's why I am going to stick with a very simple program which will simply exit itself. Alright, so let's switch to the terminal, clear everything out. Over here, let's create a new .s file and let's name it as exit.s. Okay, first of all we need to define some directives, starting with .global underscore start. This directive makes this underscore start symbol global, means it's globally visible. The reason why we need this symbol to be set as global is because if you remember, after assembling we gonna need to run another program called linker which will link all the dependencies and generate the final executable, right? So if we don't have a global start symbol, the linker will not be able to identify the entry point for this program. So we use this .global directive to define the entry point of the program. You can consider this start symbol similar to main function in C programming. Okay. Then after that, we are going to use .section directive, which specifies the section in which subsequent code or data will be placed. So normally all the assembly code is present inside .text section of the executable. So this .text section will now hold the executable instructions of a program. Then to call the exit function from our assembly program, we are going to use system calls, which are nothing but software interrupts. So we can head over to this page, Chromium documentation from Google, and over here we have all the system call numbers for all different architectures. For now we are focusing on ARM64, so let's head over to that section. And here you can see the system call name along with the registers which are used to hold the argument. So we are interested in exit function because that's what our program is going to call. So if we scroll down and keep looking for exit, there we go, we have it at 93. Okay, so to call this exit function from our assembly, we need to set this hex fd, which is nothing but 93 in decimal, into the register pointed out by this column, which is x8. Okay, then this exit function takes an argument called error code. So this error code argument we have to set in the register pointed out by this column, which is x0. Okay, let's code this. So going back to the terminal into the text section, let's define our start label. So to call the exit function, we have to move hex fd, which is 93, into x8 register, right? So for that, we have a instruction called move, another ARM developer documentation which contains information about the move instruction. So if you look over here at the syntax of the move instruction, it says move wd comma wm. Now like I said, w denotes 32-bit, right? So if you want to deal with 32-bit mode register, then you can use w. Otherwise, to deal with 64-bit registers, you can use x, right? So over here in the syntax, this wd is the destination register and this wm is the source register. Similarly, xd is the destination register, xm is the source register. But over here we are actually interested in moving a immediate value or a constant value hex fd, right? So for that, let's use this move instruction followed by the destination register, which is x8 in our case, and then the immediate or the constant value, which is 93, right? What it will do, it will move this 93 value directly into this x8 register. Okay, as we saw, the exit function takes one argument, which is the error code or the exit code, and as per this documentation or the table, this argument has to be stored into x0 register. So again, we are going to use move instruction to store the exit code into x0 register. Now this exit code could be any number, whatever you like. I am going to put 54. Okay, and then to call the interrupt, we have a special instruction called svc0. So this instruction will trigger a interrupt, and then based on these values, the operating system will decide which function to call with which argument. Okay, let's save this code. And now, as I mentioned, we have to assemble it first using arg64as command. This will take this exit.s as the input and it will generate exit.o. Now if you see, we have this exit.o file generated. This is the object file, contains intermediate code, not the final executable code. So for that, we're gonna need another tool called linker. For that we have ld. Now this linker will take this object file as an input, so let's give it, and it will generate the final executable. Let's name it as exit. All right, so now we have a new file generated called exit, and let's have a quick look at the type of this exit file using file command. It says that it's a ELF 64-bit executable for ARM architecture. Cool. Let's try to run this /exit, and it terminated immediately because that's what it is supposed to do, right? Now to make sure that it's executed as expected, if you remember, we have set the exit code, which is this one, right? 54 is the exit code. So what happened now, when this binary executed, after execution, the exit code should have been set to 54. So to check that, let me execute the binary again, and to check the exit code, we can use echo $, and now you see that the exit code, it's showing as 54, which is what we have set in our code, right? So this was a very simple program to showcase ARM assembly, and I would also like to take this opportunity to show you how the program looks like during execution using GDB. So let me clear out the terminal here, and let's load this executable in the GDB debugger using GDB exit, which is the name of our executable, right? Hit enter. It says reading symbol from exit, no debugging symbols found. Okay, cool. So the binary is now loaded into the GDB debugger. Now before running it, let's set a breakpoint at the very first instruction, and for that we first need to see the disassembly using disassemble command. followed by the name of the function which we want to disassemble. Here we have start function, right? So you see it has showed us the disassembly of this exit binary, which is exactly what we have coded, right? So during the reverse engineering, this is usually what you see either in the disassembler if you are doing the static analysis, or in the debugger if you are doing the dynamic runtime analysis. And by now you know how this move instruction works. So whenever you see move instruction, you can figure out what is going on. Like for example, over here, it's simply storing this hex fd, which is 93, into the x8 register, right? So the first instruction is actually present at this address. So let me copy this, and to set the breakpoint we can use break command and point it to this address. So it says that breakpoint 1 is now set at this address, and now we can start execution of this binary from our debugger by passing start command. Enter. Over here you can observe that the program is actually halted at this address, because that's where we have set the breakpoint in the debugger. And after that you can see all the registers starting from x0 all the way up to x30. So these are the general purpose registers which we saw over here, right? So as of now all these registers are set to 0. Okay, and after these general purpose registers, here we have the special purpose registers which we discussed in this section, right? This SP is the stack pointer which is currently pointing to this address. So this stack pointer is actually pointing to the top of the stack. We will discuss how the stack memory works in detail in the upcoming videos. For now, you can observe that over here after these registers we have a view called stack view, where it's showing us the memory stack memory. Okay, and as we saw, this stack pointer is pointing to this address, which is exactly this one, top of the stack. Okay, then the next special register we discussed was the PC register, or the program counter register, which basically contains the address of the instruction which is going to be executed. So if you observe over here, this is set to this address which is pointing to this instruction which is going to be executed next, right? And then we have CPSR or SPSR registers, which basically contains our flags such as zero flag, negative flag, carry flag, overflow flag, and so on. Okay, and after that we have a small disassembly view where it's showing us the disassembled code of our binary. So let's continue the execution by stepping over this instruction. For that we have step I command. So this will basically execute this instruction and stop at this one. Hit enter. Now you see the debugger is stopped at this instruction, and if we observe the registers now, you see the x8 register is now modified and it's containing hex fd, which is exactly what we have set from here. Similarly, if we step into the next instruction, you might have guessed what is going to happen now. X0 should now contain hex 36. Let's see. Yes, X0 is now containing hex 36. And then if we step into it further, it will trigger the interrupt, and operating system then eventually call the exit function. So you see the process is exited. Okay, so that was it. Thanks for watching, and stay tuned for the next one, where we will learn about different addressing modes and different ways in which we can move data to and from the registers, as well as storing data in the stack memory.